One of the great things about the principle of stationary action and the Euler-Lagrange equations is that they work in any coordinates. This gives us a great deal of flexibility for problem solving and is really one of the key advantages in the practical use of the principle of stationary action. Let me remind you of some coordinate systems that are commonly used. First of all, there's the Cartesian coordinate system. And this is a two-dimensional system in which points on the plane are identified by two coordinates x and y related to rectangular axes. This is the coordinate system you're probably most familiar with. For problems that have circular symmetry, it's often useful to use polar coordinates. And a point in polar coordinates, such as this one, are identified by the radius, which is the distance from the origin, and an angle, which is the angle the radius vector to the point makes with the x-axis. So again, we have two coordinates. They're just two numbers. In general, they're very different numbers than the Cartesian coordinates. We can identify any given point in a two-dimensional plane using two numbers in many different ways. And sometimes it's convenient to use Cartesian coordinates, and sometimes it's more convenient to use polar coordinates. Moving to 3 dimensions, we again have three-dimensional Cartesian coordinates. The generalization of polar coordinates is called spherical polar coordinates. In our Cartesians, we have 3 numbers to identify a point in three-dimensional space, conventionally called x, y, and z. For the spherical polars, we have the radial vector again, or radial coordinate, and we have 2 angles, the polar angle, theta, and the azimuthal angle. The polar angle is the angle that the radius vector to the point makes with the z-axis. The azimuthal angle is the angle that the projection of the radial vector down onto the xy plane makes with the x-axis. Being in 3 dimensions, we have 3 numbers, 3 real numbers, specifying the location of a point, but they can be either with respect to rectangular axes or using a radial vector and angles. Now notice that the units are different for spherical polars. The radius will be in distance units like meters, but the angles will be in angular units, that is not in meters. They may be radians or degrees. So the units are kind of mixed and you need to take care of that. In the Cartesian coordinates, everything would be in the same units, for example, meters. Important fact is that the principle of stationary action works in any coordinates. And the reason for that is just that the principle of stationary action is about paths from an initial point to a final point and finding the stationary path. That is the one on which the action only varies to second order and changes in the path. Now, in stating the principle of stationary action, you don't have to say anything about coordinates. So it's coordinate independent. So the principle of stationary action is true in any coordinates. If you choose a particular coordinate system, you can go through the derivation that we went through before to derive a partial differential equation in those coordinates, which is satisfied by the stationary path. These are the Euler-Lagrange equations. We derived them for Cartesian coordinates. That would be for 1 dimension. If we have more dimensions, we just add an extra equation for each dimension. Carrying on in Cartesian coordinates. So in 3D, we would have a set of 3 simultaneous Euler-Lagrange equations. But the really interesting thing is that if I change coordinates, for example, to spherical polars, I can immediately write down the Euler-Lagrange equations just by using the new coordinates. And that's extremely powerful. You don't have to worry about the details of a coordinate system in order to write down the Euler-Lagrange equations, which give you the dynamics of the system in that particular coordinate system. Now in the notes, I go through a demonstration that if the Euler-Lagrange equations are true in one coordinate system, they're true in another coordinate system. That is, I go through the details of how to systematically change the coordinates in the equations. Now this is a rather technical thing to do. It is very useful. Please work through the notes and understand what is being done.